Meanwhile, I'm going to
in this third talk, I'm going to expand on things I touched on just in the very last bit of Monday's lecture, particular connections of extreme electromagnetic with certain classes of minimal surfaces. And I'm going to start from the eigenvalue side, and I'll motivate it by talking about two classical theorems that many years eigenvalue surfaces, and then I'm going to be interested in the problem for surfaces with boundary, so I'll introduce the problem part 2, and then part 3 I'll describe the main theorems we have, and then depending on the amount of time I'll try to outline maybe the proof of the hardest theorem in the paper, which is the existence theorem, which I'll describe. And so this is actually a joint project with Alana Fraser, and most of what I'll talk about is in this paper. There are a few new things, but mostly there. There's also an earlier paper which introduces sets up the problem. Okay, and so let me begin with two eigenvalue theorems, one of which is very well known in differential geometry. It's called Hersch's theorem. And so first of all, just to remind you, if I take a smooth, compact surface or higher-dimensional manifold, then when I choose a Riemannian metric on the manifold, then I get a Laplace operator and a discrete spectrum Laplace. And so the eigenvalues, of course, are a function of the metric that you put on the manifold. And so this is a theorem proven by Joseph Hirsch in 1970. And it says that we consider the space of all metrics on S2, so we consider any metric, any smooth metric on S2, then for any such metric, the lowest eigenvalue times the area. So that just has the effect of normalization. So the quantity minus the 1 times the area is scaling variant. So it's a scaling variant quantity. That's bounded above by 8 pi. And equality holds if and only if the metric is a constant curvature metric. That's called Hersch's theorem. And as I say, it goes back to 1907. Okay, and so the second classical theorem, which is actually less well known in differential geometry, at least is Weinstock's theorem, which actually goes back 15 years earlier, even though the proof is almost identical to the proof of Hersch's theorem. So Weinstock's theorem actually it evolved in 2 stages. He first looked at plane domains, and then he generalized it to a kind of physical setting, which doesn't really mention Riemannian metrics, but it turns out to be equivalent to the statement for Riemannian metrics. He thought instead, in terms of actually Hersch's theorem, if you go back to the original paper, is also not written in geometric terms. He was thinking of a membrane with a density function, and then studying the eigenvalues associated with that membrane. And similarly, it's true for Weinstock's theorem. And so the statement of Weinstock's theorem, and I'll have to explain in terms of that, it says if you take, the geometric theorem says if you take any simply connected surface with boundary, so it's homeomorphic to a disk, and you take a metric G, which is smooth up to the boundary, then we have the following eigenvalue. So sigma 1 is the first eigenvalue of a particular operator, which I'll explain in a bit. It's called the first non-zero Steklov eigenvalue. And L of G is just the length of the boundary taken with respect to the G. Okay, so the statement is that sigma 1 times L is bounded above by 2 pi, and equality holds if and only if mg is equivalent to the unit disk in R2. So there's a slight thing here in that, as we see, so it's uniquely achieved by the unit disk, except for the fact that Steklov eigenvalues turn out not to really detect the metric in the interior. They depend only on the conformal class in the interior and the metric on the boundary. Okay, so that's Weinstock's theorem, and so let me, in order to explain it, let me just describe introduce the Steklov eigenvalue. So I take a Riemannian manifold with boundary, then the operator we're interested in is called the Dirichlet-Neumann map. It's actually a very important operator in several contexts, particularly in sort of inverse problems that have been applied mathematics. So what it is given a function on the boundary, let's just assume it's smooth for simplicity, then you can take its harmonic extension so that there's a unique function u hat, which is harmonic in the interior, plus u hat is 0, and which agrees with u on the boundary. Okay, and then the map we're going to consider is the map which sends u, the function u, to the normal derivative of u hat. So u is the outward normal. Surface. We have surface with boundary, and mu is the outward unit normal. Okay, so that's called the Dirichlet-Neumann map. And so that, it turns out that operator, the operator L, is, it's a global operator. So it's not a differential operator. It's actually, if you took your surface to be the upper half plane, the upper half space in general, and you take the square of the operator, you get minus the Laplacian. So it's a square root of the Laplacian on the boundary. Something like that. Of course, that interpretation is tied to the upper bound. Okay, but in any case, it's an operator, it's non-negative, self-adjoint, and it has a discrete spectrum. Its eigenvalues are called Steklov eigenvalues. So there's a sigma naught, there's one trivial one, and then all the others are positive. So the trivial one comes from constant functions. Okay, so obviously, if we take our function to be constant on the boundary, then the harmonic extension is constant, so it's normal derivative of v0. So that's in the null space of L. And so that's a multiplicity one eigenspace, and that is consistent with constant. So we'll call that trivial eigenvalue sigma naught. Okay, and the first non-zero one, in fact, all of the Steklov eigenvalues can be characterized variationally. I'm going to use the variational characterization at various points, so I'm going to write it down here. So we can evaluate sigma 1 as the minimum or the infimum of, we take functions which are smooth enough on the boundary which average to 0, so they're orthogonal to the constants, to the first the 0 eigenfunctions. And then the corresponding Rayleigh quotient is the Dirichlet integral of the harmonic extension inside, and then divided by the L2 norm squared of u on the boundary. Okay, so notice this would be, if I were doing the Neumann eigenvalue on a surface, then the variational characterization looks very similar. The only difference is this would be the integral over m, and the denominator would be the integral. So it formally looks quite similar to Neumann case. Okay, and let me just point out a simple example. So if you take the unit ball in Rm, then the Steklov eigenvalues are the positive integers, and the eigenfunctions are the homogeneous harmonic polynomials of degree k, the eigenfunctions of eigenvalue k. And so right, so in particular, the first non-zero Steklov eigenvalue is 1, and the eigenspace consists of the coordinate functions. So in particular, what's a Steklov eigenfunction? So u is an eigenfunction. Let's say on m. It means that say u is harmonic in m. So really, u restricted to the boundary is an eigenfunction. It's harmonic in m, and the normal derivative u normal is sigma times u. So those are the Steklov eigenfunctions. And so you can see that if you take a homogeneous harmonic polynomial in the ball, it's harmonic, so it's Laplacian is 0 inside. And on the boundary, when you take the normal, which is the radial derivative, you just reproduce the function of the factor k. And then you can check that in fact this is the full set of eigenfunctions. It's a complete system. Okay, so actually, if you're familiar with the eigenvalue analysis for the Dirichlet-Neumann problem on the ball, it's much more complicated than this. These are the spectrum here is extremely simple. It's the whereas if you study Dirichlet and Neumann, you have to consider Bessel functions, ODE solutions, which can't be solved in closed form. Okay, and so in a certain sense, it's the Steklov case is simpler. In fact, actually, the unit ball example generalizes to generally the case of Riemannian cones. So if you take a compact manifold and then you take a cone metric over it, then the same sort of analysis is true. Of course, the metric singular is origin, but the problem is still posed. Okay, and so let me just quickly give the proof of Weinstock's theorem, which is very beautiful. And if you know Hirsch's theorem, then you'll see that the proof is almost the same. So remember the statement here. And so the proof uses the Riemann mapping theorem. So it's the fact that any simply connected Riemann surface is conformally diffeomorphic either to the disk or the plane, in fact. And in this case, because it's a surface with boundary, it has to be the disk because it has boundary harmonic functions. So it's conformally diffeomorphic to the disk. So there's a conformal map which is a diffeomorphism. It's called phi disk. And then the idea, we're going to use the variational characterization. So the idea is then to balance the map. So we use the fact that the disk has a lot of conformal functions. So there's a conformal automorphism group of the disk, and there are enough of them to balance the map with respect to the boundary arc length measure. Okay, so what we can do is we can look at the center of mass with respect to the boundary arc length measure of the map phi. That may be different from the origin, but then we can do a conformal transformation to push it to the origin. Okay, and it's not very hard to do that rigorously. And so what we can do, in other words, is we can choose our conformal diffeomorphism to have the property that the integral over the boundary is zero. And that allows us to use the component functions, v1 and v2, as comparison and test functions in the variational characterization. And so in particular, it tells us that sigma 1 times, so I've just written the denominator on the left-hand side, sigma 1 times the L2 norm squared over the boundary is less than or equal to the Dirichlet unit of inside. Now in this case, the phis were already harmonic. Map. So this is just being a little crazy phi squared. And then I just add them up. So if I add I equals 1 to 2, then our conformal diffeomorphism takes the boundary to the circle, the unit circle, and so the sum of the squares of phi is 1 on the boundary. So when I add up, I get sigma 1 times the length. The right-hand side gives me the energy of the map. And for a conformal map, the energy is 2 times the area. So it's a conformal map. So the area is the integral of the complex derivative squared. And that turns out to be just half of the sum of the gradient of phi squared. And so that's 2 times the area of the image. Is the area of the image. The image is the unit disk, so the area is pi. So that's the proof. It's a very beautiful and elementary proof. Okay, and the proof of Hirsch's theorem is pretty much the same, except you use the uniformization theorem, the fact that any metric on S2 is conformal to the standard one, and then you use the conformal automorphism group of the sphere, to do the same sort of procedure. So they're really very parallel ideas.
Actually, Rick, the idea was still the same.
What's that?
The idea was still the same.
Well, Zago's estimate for the Neumann eigenvalue was published the same year as Weinstock. I've never been able to sort out the connection between Weinstock and Zago. Weinstock was also in Stanford at that time, so they must have known each other, but Weinstock didn't refer to Zago or vice versa.
Zago's work was very early, 1930s, I think.
This is published in 54. I think Zago was around 55.
I thought Zago was earlier.
Yeah, I know. It's an elevated.
But anyway, Hirsch argument just followed from them finally. Hirsch argument Hirsch.
Yeah, it's a similar argument.
But nobody referred to Zago or Weinstein anymore.
Right, that's true. So I think this case was not that well known.
Yeah.
boundaries. They never considered circular boundaries. Okay, right. Okay, so so then based on Hirsch's theorem first, it's very natural to try to extend this to other surfaces, right? So you can say, suppose I take a smooth surface which is not S2, which is a torus or a higher genus surface, then can I maximize? So if I fix the area, can I maximize lambda 1? Okay, and actually there's really a lot of literature on this. It's a rather non-trivial problem. The first result, which was done beyond the two-sphere, was the case of RP2. Oh, sorry. The case of RP2, which was done by Li and Yao in the early 80s. And again, it's true there that the constant curvature metric is the unique maximum for the real conventional. And then the torus case was solved by Nadarashvili in 1996. So it turns out the answer again is a constant curvature metric. It's a constant curvature metric on a 60-degree equilateral torus. So it's a sort of the most symmetric torus. So it's torus generators of equal length. So in particular, it's not the Clifford torus. The answer is not the Clifford torus is sort of a critical point for the problem, but it's not the maximum. Okay, and so actually there's also a series of papers on the case of the Klein model, and so in this case there's a metric which is not flat, but it's gotten by solving ODEs and S1 invariant metric, and there's a series of papers which characterizes. Shows that this is the unique maximum for Klein model. And then actually just about a month ago, there was a paper, well, let me just say by the way that the case of the torus and the Klein model are in some sense much harder than the sphere and the RP2 because the way the proof proceeds is to first prove the existence of the maximizing metric and then to characterize it. And so that existence theorem turns out to be quite difficult. It's in the 1996 paper with Nadarashvili. In fact, if you talk to many experts in the area, they don't really understand that. There's a paper posted a few weeks ago by Harkugan, who claims to determine the extremal metric in the case of a genus 2 surface. So there was a conjecture made by Nadarashvili, Polterovich, Jacobson, another author, that the genus 2 case should be maximized by a metric which is the pullback of the metric on S2 for a particular complex structure on a genus 2 surface, got by pullback of a branch covered in S2. So it would be a metric whose curvature is 1 except at branch 1. So it's a bit odd that maximizing metric is kind of degenerated in the genus 2 case.
Well, you know, we used to mention I wrote with Paul Yen.
What's that?
You should mention I wrote with Paul Yen.
Okay. Yeah, I'm not going to talk about how the
No, this is first time I've done
right.
that.
So the fact that there's an upper bound was done by Yang and Yao. So of course it's important first that there be some upper bound depending on the topology. And so that's the okay. So I'm going to now move away from question.
Maybe you talk about S2 or torus, and
Yeah.
in this picture you have this sheet with monochrome and hand.
Right. So this is the case for compact surfaces, closed surfaces. I'm going to talk about surfaces with boundary. So I didn't draw this picture. This is supposed to be a surface with boundary. So this is the map. This is the map. Yeah. So this stuff has to do with closed surfaces without boundary, and I'm going to talk about I'm going to talk about boundary next. So I'm just giving this as background for what I have to say. Okay. So, okay, so so me first make an elementary point. That is that if we consider orientable surfaces with boundary, then there are two integers which classify them topologically. One is the genus and the other is the number of boundary components. So for example, this is a surface of genus 1 with a single boundary component. That's because if I fill in the disk, then I get a torus for a genus 1 surface. So in general, any orientable surface with boundary is gotten by taking a closed orientable surface and moving a finite number of disks. So the number of disks is K, the number of boundary components. And so in particular, Weinstock's theorem classifies, it gives the extremal for gamma 0 and K is 1. So that's the disk. Okay, and so the question is what happens for more general surfaces with boundary? Okay, and so in particular, we can pose the question, given a smooth surface with boundary, is there a smooth metric which maximizes sigma 1 times L, and if so, can you describe it in some cases? Okay, and as stated, this is a really difficult problem. It's very far from being generally solved, but we have some interesting results on this. And I'll describe it. Okay, so first of all, we can first let's assume formally that we have a maximizing metric on our surface with boundary. So we can first say, let's structure that imposes on the surface. And it turns out that this is where the connection with minimal surfaces comes in. So if we assume that we have a metric G, which is where sigma 1 L is maximized, let's say it's a smooth metric. And then what happens is it always has multiplicity of at least 2. So it turns out multiplicity 1 metrics, which are generic ones, never maximize. So the maximizers always have multiplicity. And you can construct, you can find n independent eigenfunctions if you want n for some n greater than or equal to 2. So you can find a map if you want n, and we think of this as a map from m into Rn, but it actually has values in the unit ball. So this is the unit ball in Rn. That way. And this is a proper map. These are first eigenfunctions, T1 to Tn. Moreover, it's a conformal map. And of course, because they're eigenfunctions, it's harmonic. Because the eigenfunctions are harmonic inside. And so we get a conformal harmonic map, a proper map to the ball. And then the Steklov boundary condition is the condition that the image, if I take sigma, which is the image surface, V of m, it's the condition geometrically that the surface meets the boundary orthogonal. So this is the class of surfaces I considered in Monday's talk. So that's the general situation. So if I can find a maximizing metric, then I can always arrange that eigenfunctions which give me a proper branch minimal immersion to the ball with the orthogonality condition. So that orthogonality condition is just the Steklov boundary condition. And moreover, the metric G, the extremal metric, is really the induced metric. It's in fact the extremal metric G is equal to the positive constant time induced metric. So generally, of course, sigma 1 times L is scale invariant, so I can only expect the metric to be determined up to a positive constant. Okay, so in other words, we can see the extremal metrics of this problem as the induced metrics on free boundary minimal surfaces. So that's the general result. And I actually have a proof of it here. It's actually a rather interesting result. This theorem, I should say, is an analog, which it's a pretty direct analog of a result of a non-irrationality in that 96 paper. So the corresponding thing for closed surfaces is that you get a conformal, a minimal immersion into a sphere instead of a ball. So it's a rather interesting proof. I have an outline here, but I wonder if I'll do it. Maybe I'll.
Can you explain more the last line that the G is the positive constant times the induced?
Yeah. So I have that. Right. So I have my extremal metric G. So I'm starting with a surface with a metric, right? And so And now I have two metrics. One of them is G, the extremal metric. The other is the induced metric from Dn, from the ball. Right? So that would be the metric E star of the Euclidean metric relative. That's the induced metric as a surface. And the claim is these two are the same. They're the same up to a constant on the boundary. So in other words, the surface is conformally equivalent to the surface we started with, and the metrics on the boundary, one is a constant times the other. So that's really the uniqueness statement for Steklov eigenvalues. Because you see the harmonic function theory in 2 dimensions is conformally invariant. And so the Steklov eigenfunctions can only detect the conformal structure inside and the metric on the boundary. And so this is really the natural equivalence for the problem. So maybe I just say a few words about the proof. So again, it's an interesting argument because if you just think of the eigenfunction as a variational problem, the eigenvalue as a variational integral, then of course it's not smooth. It's not a smooth function of the metric because when you have multiplicity, the eigenfunction, it's only a Lipschitz function of the metric in general. And so you can't simply formally take derivatives and expect to get the right answer. But the first step in the proof is to formally take derivatives. So you first consider, suppose we had a smoothly varying family of eigenvalues and eigenfunctions, and we call it sigma t. And I suppose I have smoothly varying eigenfunctions, and I normalize them so that the integral of u squared on the boundary is 1, which I can do. And I also fix the boundary line. So I take a family of metrics gt, and suppose, for the sake of computation, that I can, near t equals 0, I have a smooth family of eigenfunctions, and I fix all the metrics have the same boundary. Okay, and so I want to differentiate sigma of t. I want a formula for that. So the easiest way to do that is to write it in variational form. So the eigenfunctions satisfy this condition. This is sigma t, this is sigma squared. Okay, so we have a path of metrics. So we'll denote the derivatives at time 0 with a dot. And then when we compute so we just have to compute the derivatives of both sides, and we'll normalize the integral of u squared at time 0 to u1. Well, when we differentiate the t dependence here, there are several different t dependencies that depend on this. There's the dependence of ut, the fact that u is changing. There's of course the eigenvalue one which we're going to compute, and there's also the ones coming from the metric. So the area form and the norm squared depends on the metric and the length on the boundary does. Now, because u is a critical point at time 0, the dependence on ut cancels out. So when I differentiate the ut part, I get 0 because of the eigenvalue condition, eigenfunction condition. So the only thing I need to differentiate is the metric dependence here. And so this, if you write it out explicitly in terms of the metric, looks like g upper ij times du dxi dxj, and then times the square root of the determinant g dx. So when you differentiate that expression, you get so h is g dot, is first variation. You get actually, this is sort of a little bit related to relativity. So if you think of u as a scalar field in relativity, you get the stress energy tensor of that scalar field. This is one of the ways of computing the stress energy tensor. So what that is it's a symmetric tensor, which is first derivative tensor with itself, ju, and then minus a trace term, it's 1/2 of the squared. So the trace term comes from differentiating the volume area, and the other one comes from differentiating g upper ij. And then the differentiating the boundary term gives us the integral of u squared times h of tt. So it's just h applied to the direction of the unit tangent. Okay, so that's the first step, is to derive the formula. Okay, and now we have to deal with the fact that we can't expect to have smoothly varying families of eigenfunctions. And so the picture is really more like this. So if we have multiplicity,